To Math 331 problem solving. This is lecture 11. And so one of the nice things about this class is we can adjust what we're doing based on comments in class. If there are things you want to see, you can let me know. If there are things I want to see, I can put them in. And I got intrigued by some of the questions we had yesterday. In particular, is it possible to have two Pythagorean triples with the same hypotenuse but different bases in a non-trivial way? 3, 4, 5, 4, 3, 5, I'm not going to consider that distinct, right? So we typically say, let's order them so the sides go from smallest to largest, something like that. Can you have two fundamentally different pairs of sides? And we came up with a way to show that, yes, it's possible by explicitly exhibiting a solution. That's a great way to prove you can do something. Rather than giving a long proof, actually give an example that someone can see. Very hard to argue with that. If you have a theoretical proof, the proof might be right, but that's going to be a lot more work to make sure everything is correct. If you can give someone a constructive example, once you have one example, then the question becomes, can you construct infinitely many non-trivial? I can multiply every side by 5, by 6, by 7, and it's still going to be a triple that works. I don't want to consider those new solutions. So you often have some kind of condition where you assume the sides are relatively prime. Something like that to make them fundamentally different. And so what we did last time gave one example. Are there infinitely many examples? And so we're going to do an easier problem today to start. I do not think we'll get to the problem we were talking about on Friday. Can you give me two different sides that are integers that have the same hypotenuse? So the only difference between that and what was asked is that I'm no longer requiring the hypotenuse to be integer. It just has to be the square root of an integer. Okay? So does anybody know off the top of their head two different sides that work? So we're basically saying is, can you give me an integer that can be written as the sum of two squares in at least two different ways? And we're not going to consider 3 squared plus 4 squared equals 5 squared and 0 squared plus 5 squared equals 5 squared. I'm not going to let you do something like that. Otherwise, any Pythagorean triple would work, and one of the entries would just be 0. So that's the goal today, is can we find something like that? So find, say, a squared plus, let's say a1 squared plus b1 squared equals a2 squared plus b2 squared. Without loss of generality, ai is less than or equal to bi, and a1 does not equal a2. Yes. Oh, it's not showing. Oh, it's not showing. Sorry about that. Okay. So can we find two different pairs of integers such that the sum of the squares are the same? And I can order them in such a way if I want so that the first component is always going to be the smaller of the two. Okay? And we want each to be a positive integer. We know it can be done because we did it last time where the sums of the squares was actually a perfect square. So it's definitely going to be doable. And so the reason I like this is this allows me to introduce one of my favorite mathematical problem-solving techniques. Hopefully you've heard of this before, and we will see it very shortly. So everybody is familiar with clock arithmetic. There's actually even a clock in this room. It is roughly 10 o'clock now. What time will it be in 5 hours? This is not a military classroom. This is an academic. 10 plus 5 equals on a clock with 12 hours. So actually, we're going to see two great proof techniques today. And really what we're doing is A plus B is congruent to C mod M means there exists an integer k such that A plus B equals C plus K times M. That's what it means to be equivalent on a clock, is you differ by some integer multiple of the number of hours. Okay, so now let's look at sums of squares. And we can choose how many hours our clock has. We could take a clock with 2 hours. So it's 0 or 1. That's going to be a little bit boring. So we're going to start off with a 4-hour clock. We'll do an 8-hour clock, and maybe we'll even do a 16-hour clock. If we do a 4-hour clock, our numbers are 0, 1, 2, and 3. And what are the squares going to be on a 4-hour clock? So if my numbers are 0, 1, 2, and 3, when I square 0, what do I get on a 4-hour clock? 0. What do I get when I square 1? What do I get when I square 2? 0, right? What do I get when I square 3? 1. So now, if I look at sums of 2 squares, what are the possibilities on a 4-hour clock? I've got 0 and 1 are the only values for squares. So I have 0, 1 plus 0, 1. What are the possibilities? So what do you think the possibilities are? That's the only possibility. I have 0 and 1 for the first component. I have 0 and 1 for the second component. What are the possibilities for the sums? I could have 0 plus 0 is 0. What else could I have? 0, 1, or 2. So what do you observe does not happen when you look at the sums of 2 squares mod 4? So what do we notice? The possible remainders mod 4 is 0, 1, 2, and 3. But when we look at sums of squares, we only see 0, 1, or 2 as possibilities. What can you deduce? Can every number be a sum of 2 squares? So if I'm a sum of 2 squares, my remainder when I divide by 4 is either 0, 1, or 2. Can every number be a sum of 2 squares? Which numbers can't be sums of 2 squares? So which numbers cannot be sums of 2 squares? Numbers that are 3 mod 4. We just showed that if you're a sum of 2 squares, your remainder when I divide by 4 is 0, 1, or 2. So you can't get 3, you can't get 7, you can't get 11. So we never get 3 mod 4. So we miss what percent of numbers? So we're looking at sums of squares mod 4, and we just showed that if you look at sums of squares mod 4, you get a remainder of either 0, 1, or 2. So we just showed you never get a remainder of 3 mod 4. So minimum, what percent of numbers cannot be the sum of 2 squares at a minimum? 25%. Miss at least 25%. We might miss more, but we know we have to miss at least 25%. We could look at an 8-hour clock. So now, what are the possible remainders? 0, 1, 2, 3, 4, 5, 6, 7, 8. When we look at n squared, 0 squared is 0, 1 squared is 1, 2 squared is 1 o'clock with 8 hours. What's 2 squared? 4. What's 3 squared? 1. And in fact, we know that it repeats because if I look at 8 minus x and I square that mod 8, that's the same as x squared mod 8. So I know it's going to repeat. So 4 squared is going to be 0. 5 is just the same as 8 minus 3, right? So that's just negative 3 squared, which is just 1. 6 is just going to be 8 minus 2. So it's just going to be 4. 7 is the same as 8 minus 1. So that's just going to be 1. And then 8 is 0. So it just repeats. So now when you look at sum of squares, how many possibilities do we have for the first one? It's 0, 1, or 4. 0, 1, or 4. What are the possibilities now? Zero, 1, 2. What else? 4, 5. But 8 is the same as 0. So what can you deduce? Not all numbers are sums of 2 squares. We miss 3, 6, and 7 mod 8. So miss at least what percent? Three-eighths. Who can do the math? 37.5%. So notice if we looked at things mod 4, we know we miss at least 25%. We might miss more. Looking at things mod 8, we see we actually do miss more than 25%. We miss at least 37%. Building on the success of 4 and 8, and given the fact that I've written m equals 16, what might you try next? Right. It should be pretty obvious to try m equals 16. And after m equals 16, what should you try? So we missed 1/4, then 3/8. Or another way of looking at it is we had at most 3/4, and now here's at most, what is it going to be, 5/8? Which pattern do you think is easier to look at? They're really the same, what you miss or what you get. 3/4, 5/8, what would you guess for the 16ths? How many do you think you have? How many do you think you miss? I'm sorry?
1/2.
You think it's going to be exactly 1/2?
Oh, actually, no, then it's going to drop to 0. No.
So we have 3/4 that we got when we had m equals 4. We had 5/8 when we had m equals 8.
We had at most 9/16.
So do you think it's 9/16?
Or 7. Well, like the pattern does kind of make sense where like you start off with m equals 4 case and then you double like you double it and then you subtract 1 from the numerator and then you
So is it 1 more than half? So if we have 16ths, half of that would be 8/16. 1 more of that would be 9/16.
Yeah.
So again, 2 data points, it's kind of hard to determine what's going on with just 2 data points. I would like a 3rd data point. I believe if you do another one, you do get 9/16. And it's going to be just a little bit above 50%, and it's going to be heading to 50% from above. And so if we do this, we're going to be able to get better and better bounds, but there's a limit to how well that this is going to go, unfortunately. So what I did is I wrote some code in Mathematica. And so what this does is you give me a modulus, and I can decide whether or not I want to print things out or not, and it will go through and it will calculate how many distinct sums of squares do we get? For summing two different squares. What fraction of the residues are hit? And so this is set up so you give it a modulus and it will go through and it will tell you. If you want to do a range of moduli, then what you do is you just write another program that just calls it. Try to have things with good names, mod tester. Okay, that should hopefully be clear what this is doing. And then it will just run through and it will just save results and it will print things out. Why is this useful? Well, the idea is we're trying to show that there must be multiple bases that have the same hypotenuse. We're trying to show that there are two different pairs of bases for right triangles, such that their sum of the squares is the same. If we can show that there are fewer and fewer and fewer possibilities, and we have more and more sums of squares, eventually there has to be a collision. We have to have two pairs giving the same thing. Does anybody know what principle I'm trying to use? It has at least two different names. I want to show that if I have very few boxes and I have a lot of items that I'm trying to put in, there has to be a collision. Pigeonhole. So this is either the pigeonhole or the box principle. And sometimes they add Dirichlet's name to it. Has anybody here not heard of the Dirichlet box principle? Okay. It's the same thing as this. So basically the high level is you have n boxes, n plus 1 pigeons, and you shoot the pigeons into the boxes. No pigeon is hurt when doing this. They have nice, comfortable landings. Everything is fine. At least one box must get at least two pigeons. If each pigeon is assigned exactly one box, at least one box has at least two pigeons. It is amazing how powerful this observation is. And the proof is basically, if this were not the case, if not, then each box has at most one pigeon, only accounts for at most n pigeons. So the whole point is that if I have a small number of boxes and a large number of items, and everybody is put into some box, at least one box has to have at least two items. Is it possible that only one box has two items? Yeah, give me a way that only one box has two items.
One box has two, the other ones all have one.
So that's one possibility, yes. There's another way, even more extreme.
All
All of them go into one box, right? There's multiple ways for it to happen. So no matter how many pigeons I give you, as long as there's more pigeons than boxes, at least one box has at least two pigeons. It is possible if I give you exactly n plus 1 pigeons that I do exactly what you said. One box gets two, everything else gets one. So it's possible that I might not do better than this. It's possible that I could have a box with 3 pigeons. It's possible I could have multiple boxes with 2 pigeons. How is this useful for what we're trying to do? We're trying to look at how many ways can I look at sums of 2 squares? Well, sums of 2 squares have to have values. And I want to try to show that at least 2 different pairs will have the same sum of squares. And so if I look at the sum of the squares modulo some number of hours on a clock, if I don't have that many possibilities, then the hope is that I have to have at least 2 of them going to the same thing. So that's how we're going to try to use it here, is we choose sum modulus m, look at sums of squares mod m, assume the sum is less than or equal to x. Okay. Is every possible residue realizable as a sum of two squares for a given modulus? Not necessarily. We've actually shown that there are some moduli where a lot of residues are not possible. We saw some moduli miss a lot of residues. Find a good, or if you want, you could call it bad, modulus where you miss a lot of residues. Where you miss a lot of residues. The hope is then two pairs go to the same thing. Okay, because we don't, if we miss a lot, imagine we missed 98% of all residues. I want to then somehow use this to conclude that I've got to have a collision somewhere. It's okay if all the details aren't clear right now, but is the general idea, is this beginning to make sense? That one way to show I have two different pairs that have the same sum is to show there's not that many possibilities for them to live in. And if there aren't that many possibilities, and I have a lot of things coming in. So of course, the question is, how many things do I have coming in? So question, let's say we have a pair NM with 1 less than or equal to, no, I don't think I've ever written this down anywhere. So N, oh, I don't want to use M. We'll do X and Y. I don't want to do X and Y. We'll do A and B. With 1 less than or equal to A, less than or equal to B, less than or equal to square root of X. And we want A squared plus B squared to be less than or equal to X. So my question is, how many pairs do we have? Can anybody give me an upper bound? It's okay if the upper bound's not great. So I want to look at how many pairs A and B with A squared plus B squared less than or equal to X. X, why did you get X? So that is a horrible upper bound, but it's correct and accurate. It's completely useless because we're trying to show that two pairs have to align. How many numbers are there from 1 to X? X. And we show that there's at most X pairs. Is it possible that they all avoid each other? Unfortunately, yes. We miss by 1, right? So your upper bound, that there's at most X pairs, is not good. But of course, we really need a lower bound. I could give you there's an upper bound of X to the 5th pairs. And if there's X to the 5th pairs, then there's going to be a tremendous number of overlaps, but I don't necessarily have X to the 5th pairs. So what we really need is we need a lower bound, not an upper bound. So if there really were about X pairs, we would have just missed. But do we know that all possible values from 1 to X are realized? What fraction of the residues are realized? What's our best result to date? 9 over, we never actually proved 9 over 16. We're conjecturing. We did prove 5/8.
Yeah.
So we know we lose at least 37.5%. So if we could show, for example, that there were 60% of X pairs, 0.6 X pairs, then that would be enough to know there has to be an alignment. So what we really need is we need a lower bound. And we'll get to that in a little bit. I thought I would give you a little bit of data first. And this is why, I did cheat a little bit and I did do some calculations at home. And so I ran the code, I modified it ever so slightly so that rather than doing all moduli, I just had to do powers of 2. And I just formatted things nicely so it looks impressive. I drew a solid red line because I like drawing solid red lines. And you can look at the probability. This is not a proof, but if you are looking at this data and you're not conjecturing that it's converging to 50% from above, we need to talk. And I'll drop whatever I'm doing and I'll find time to meet with you, okay? This is almost as clear as possible. The numbers are getting smaller. You could even do some calculations and try to figure out how are they approaching. Writing these numbers as fractions is a very bad idea. How should I be writing these? I'm sorry, as decimals, sorry. Writing these as decimals is a very bad idea. I should be writing them as fractions. And then you should hopefully be seeing, okay, there's the 3/4, there's the 5/8. The next one, do you think that's 9/16?
Yeah, the difference halves.
So it looks like the difference is having, and it looks like it's basically, if you have 2 to the k, it's 1 more than 2 to the k minus 1. It's 1 more than the halfway point. So it really is looking like what you would expect. I looked at, which ones is this? I looked at the Fibonacci numbers because I'm the president of the Fibonacci Association. So whenever possible, I have to try to bring the Fibonacci numbers into the conversation. And when you look at this, the number of residue classes that you get, it's 100% most of the time. There are 2 values when it's not 100%. Anybody want to guess what those 2 values are? So the Fibonacci numbers I'll do it as 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. So 140, so this one is 144. So it's a perfect square. And anybody want to guess what this one is over here? Look at the Fibonacci numbers. 1, 2, 3, 5, 8, 13, 21, 34, 55, 89. What do you think that number is? You already know this. We've done this.
2.
Nope. Probably 8. 2 would be 100%. Right? We did that 8 gave us, I think, 3/5. No, sorry, 5/8. 5/8.
Yeah.
So we knew that it wasn't 100% at 8. So 8 is a power of 2. 144 is a perfect square. This is the danger of having a very small set of data. So I'm reading Nate Silver's The Signal and the Noise right now, which is an interesting book. And if somebody tells you after the fact what happened and what data to look at, you can see the relationship. It's beforehand, that's the interesting thing. And so here, I'm deliberately giving you small amounts of data. What's special about the numbers 8 and 144? There's a lot of properties about them. How would you try to figure out what's special about them? What should we do? Good, find more data. So as a rule of thumb, one of your responses whenever you have a problem to solve is collect more data as long as it's not too hard to do. There's always the danger of paralysis by analysis, and you spend all of your time gathering data and you don't actually do anything. But if you can gather more data quickly, and so on, then so I think the next one is I looked at a large amount of data up to 300. And I found the solid red line is 50%. And I found a couple of values that were below 50%. So that meant a majority of the residues could not be written as the sum of two squares. And this is just displaying what they are: 72, 144, 216, and 288. If you know Mathematica, you might be able to figure what the stuff on the far right is. Any thoughts, anything that you notice about these numbers? So what do you notice about 72, 144, 216, and 288? Okay, they are multiples of 24. Good, what else? You can be stronger than just multiples of 24. They are multiples of 72.
Are those to the third and 3 to the...
Yeah, these are the factorizations of those numbers. So the first, so 72 is 2 cubed 3 squared. 144 is 2 to the 4th 3 squared. What do you notice about the factorization of these numbers?
Product of square? No, product of power.
Which powers? So whenever it was below 50% for the first 300, it only had 2s and 3s as factors. Do you want to conjecture that this continues?
Sure.
How much do you want to? So now in the now you've read the Nate Silver book because you look like you're
read his
nodding.
next one.
Okay.
It's any references.
Okay. Okay.
Should I
So-
read Signal and Noise?
I would say yes.
Okay.
And so one of the things that he talks about is it means nothing if you're not willing to bet.
Yeah.
Now, again, I've done the calculation ahead of time, so I am quite willing to bet on this one. I will not tell you which way I will bet, though. Would you put money with 4 data points?
Yeah.
No, right? What range would you like me to go up to for you to be comfortable? 100,000. That will take a while.
Yeah. You like 1,000.
So let's go up to 1,000. I think I can do 1,000.
Oh wow.
So I went up to 1,000. And we got a couple more points. And oops, here are the numbers and the factorizations. And so what you notice is there's 360, which has 5. There's 504, which has a 7. So other ones are coming up. This is how research happens. I have no idea what's known for this problem. But all of a sudden, we're getting into potential research projects. People are thinking about small or summer research. These are some things we could start to look at. Then the question becomes, which number gives us the best? Any thoughts?
I bet that it should be just the product of primes.
But which product of primes? Which?
It's 576. It's in red.
Yeah, exactly. I mean, I've got 576 in red, right? So if you look at the percent of residues that you hit, 576 is the smallest I've seen, up to a little bit more than 1,000. I think I went up to like 1,024, 1,025, something like that. So I got up to 40.1042. That's not bad. So the question is, what's the smallest? Can you do something smaller than 40.1042? And what smallest do we need? So let's see. We need to count the number of pairs A, B with 1 less than equal to A, less than equal to B, less than equal to square root of X, and a squared plus b squared less than or equal to x. I want to know how many pairs there are. Right? So this is what I was doing while walking yesterday. So I am going to do the calculation roughly. Okay, I'm going to make a couple of approximations, and so I just want to get close. All right. And here we go. So we have the sum, b goes from 1 to what's the largest b could be? Square root of x. And now what's the largest a could be? Well, but I want a squared plus b squared to be at most x. So how large could a be? The square root of x minus b squared times 1, because I'm just counting this. So does everyone agree that that counts how many pairs there are? This is, and again, I'm going to just do approximations. This is approximately the sum b goes from 1 to the square root of x of the square root of x minus b squared. Yes? And what is this sum approximately equal to? Another proof technique, another problem-solving technique. How can I approximate this sum? How can you approximate a sum? You've taken 1 to 3 classes on this. What do you have to approximate a sum with? I'm sorry? An integral. This is approximately the integral b goes from 1 to the square root of x of x minus b squared to the 1/2 db. Right? This is, your Riemann sums. And because this function is nice, this shouldn't be a bad approximation. All right, I want to change variables. I want to try to figure out how does this scale with x. So I'm going to change variables. Anybody have a thought about how I should rewrite the variable b? I want to figure out the x dependence. I've got the square root of x minus b squared. How should I write b? So we talked a little bit about rescaling earlier in the semester. This is one of the key ideas. We did this with some of the integrals. Look at it, we have two terms. We have x minus b squared. So if I want to write b in terms of x, what power of x do you think b should be like? I'm sorry? Not x squared, square root, because I've got a b squared. So if b is of order square root of x, then b squared is of size x. I should write b as t times the square root of x. So db is going to be root x dt. And then b goes from 1 to square root of x, becomes t goes from what? What does t go from? 1 over square root of x,
Yeah.
which is 0, to what? To 1. So the integral is approximately, or our sum is approximately the integral t goes from 0 to 1 of the square root of x minus xt squared, x to the 1/2 dt. I can pull out a x from the square root, which gives me an x to the 1/2 times x. So that's going to give me x, then the integral from 0 to 1 of the square root of 1 minus t squared dt. And notice I'm trying to count how many pairs there were. You had the upper bound of x for the number of pairs. What can you tell me about the integral of the square root of 1 minus t squared from 0 to 1? What can you tell me about the value of that integral? Really simple, weak answer. It's at most. It's at least 0. What's it at most? It's at most 1. So this is giving you an upper bound of this at most x pairs. Great, things are consistent. And this is going to tell you how many pairs you actually lose. Because again, if A and B are both very large, if they're both, say, 7/8 root x, then their sum of their squares is going to be too large. So you're not going to have x pairs, but you're still going to have on the order of x pairs. So the upper bound, we know it's at most 1. Does anybody remember how to integrate the square root of 1 minus t squared? So much fun.
You're allowed to split it into 2 parts.
It's integration techniques.
It's a while.
USUP.
Yeah, I've read all of it.
What should you take for t to be? T is,
Wouldn't it be like 1 minus t squared?
you could do that. I think there's something, I mean, it's essentially the same, but then your du is going to be painful. Instead of u sub, it's a special case of u sub. Just seeing who remembers their integration.
Well, does that have?
So can you think of any relationships where 1 minus something squared is the square of something nice?
Yes, cosine sine.
Yeah, cosine sine. Do you want t to be sine or cosine? It starts at 0 and goes up to 1. So do you want that to be the sine or the cosine? Sine. So take t to be the sine of theta. Then t goes from 0 to 1 becomes theta goes from 0 to pi halves. So now we have that the integral is, the sum is approximately integral, so we're going to get x, then we'll have the integral theta goes from 0 to pi halves, the square root of 1 minus sine squared theta, and then dt, what's the root of sine? Cosine. So it's going to be cosine theta d theta. Cosine theta d theta. So this is just x integral from 0 to pi halves cosine squared theta d theta. Anybody remember the antiderivative for cosine squared? So you can do the cosine of 2 theta is cosine squared minus sine squared. So cosine of 2 theta is, oh dear Lord, 2 cosine squared minus 1. So cosine squared is 1/2 cosine 2 theta plus 1. You could do that. That's one way to do it. So you could use cosine of 2 theta is 2 cosine squared theta minus 1, or cosine squared theta plus sine squared theta equals 1. So this is the same as x times 1/2 the integral from 0 to pi halves of cosine squared theta. This is a wonderful trick. Sine squared theta d theta. Okay. Because in the interval from 0 to pi halves, sine squared and cosine squared cover the same thing. So what does this integral equal? Pi over 2. And so then this becomes pi over 4. So x times pi over 4.
Can I ask you one thing?
Yes.
The green line, the second green line. How do you pull x out of the integral, not x? The root of x?
Oh, sorry. I did pull out the square root of x, but I also have an x to the 1/2 dt. So the x to the 1/2 and the x to the 1/2 reinforce. We have an x to the
Yes.
1/2 dt. When I pull out the square root of x, square root of x times square root of x is x. So this x over here, this is coming from Okay. So I'm just wondering if I've dropped a factor of 2 somewhere. I feel like I dropped a factor of 1/2 somewhere. Okay, so this gives me pi-4ths as the number of pairs. With a, b, with a less than equal to b less than equal to the square root of x. Is this a reasonable answer?
That's what, like 78%.
So 3/4 would be 75%. So this is a little bit more. So so let me see if I can quickly. All right, so let me try. Okay, so let's see, is this showing screen here? Oh, shoot. It is. Oh. No, the issue is if I try to share it like that, it's going to cause an issue. All right. I think I'm off by a factor of 2 right now from what I had at home.
The integral is correct. It's pi over.
Well, I'm sorry?
So the integral of what's square root of
Right,
pi
right. Right. So what I'm wondering is, am I missing? Well, so let's see. For let's say a equals what's this? b equals 1, b less than equal to 1,000, b plus plus. For a equals 1, a less than equal to b, a plus plus, and then if a squared plus b squared is less than equal to, so we were having both of them go up to the square root of x, so this would be up to 1,000 squared, then count equals count plus 1. And I'll initialize count to be 0. And then let's print count. And so we'll also print pi divided by 4. So did we drop a factor of 2 somewhere? Oh, sorry, not this one. Okay, so if I multiply by 2 for the counting, then I'm basically getting pi over 4. So there seems to be a factor of 2 that I am missing. And so all right, so are we missing a factor of 2? I'll try to finish this really fast. Does anybody know what pi over 8 is approximately? It's close to that. So pi over 8 is 0.392699. And the best we had when we were looking at the data was 0.401. So it just misses, if that factor of 2 is there as it's supposed to be, it just misses giving us an elementary proof that there's a collision. We have just a little bit too many residues if it truly is pi over 8. And I apologize that I seem to be missing the factor of 2 right now. I'll think about that later. But this is what I'm going to have you guys do as a challenge. Can anybody find a modulus that does a little bit better than 0.401? We need to beat 0.392699. And looking at the first 1,000, it just barely misses. And this is why I was so pissed off that I couldn't do more work with this until today. All right, so I apologize that it did not quite work out at the end. Part of it is deliberate. I want you guys to finish.